Hey gang, today we're going to be looking at geometric sequences. Exponential functions are also geometric sequences. The input, or x, represents the term of the numbers in the sequence, and the output, or y, represents the number in the sequence that follow a pattern. A geometric sequence is a set of numbers that follow a multiplication or division pattern, like we saw with exponential functions. So let's consider the following. If we have this table, the first term is 3, the second is 12, the third is 48, and so on. This is a geometric pattern as there is a pattern of multiplying by 4 in the second row. So if we do 3 times 4, we get 12. If we do 12 times 4, we get 48. 48 times 4 is 192, and 192 times 4 is 768. So this is a geometric pattern or an exponential function. Formulas. The explicit formula, again, is a formula that can be used to find any term in the sequence or to determine what term a number is in the sequence. So similar to arithmetic sequences, we can address it in either one of these two ways. F of n equals f of 1, which is the first term, times r, which is the common ratio, to the n minus 1. And a of n equals a of 1 times r to the n minus 1. Again, having the first term and the common ratio in the problem. Then a recursive formula is a formula that can be used to generate a sequence given the first term. So again, in two different ways, f of n equals f of n minus 1 times r, where the first term is given, and a of n equals a of n minus 1 times r, not d, where the first term is also given. And f of n minus 1 and a of n minus 1 are the previous term. So we're plugging in the term before to get the next term. So using the above table, the formulas would be f of n equals 3 times 4 to the n minus 1. And the recursive formula would be f of n equals f of n minus 1 times 4, where the first term is 3. Because we're multiplying by 3 repeatedly, we're multiplying by 4 repeatedly, and we start with 3. Okay, so let's take a look at some examples. So here we have two tables, again, that we need to look at to figure out if we can see a pattern that is geometric, meaning that's multiplying or dividing in nature. So if we go from 5 to 15, we're multiplying by 3. 15 times 3 is also 45. 45 times 3 is also 135. And 135 times 3 is also 405. So explicitly, or just explicit, this would be f of n equals 5 for the first term times 3 repeatedly to the n minus 1. And recursively, this would be f of n equals f of n minus 1 times 3, where the first term is 5. So if I plug in 5 here for that whole thing, 5 times 3 gives me 15, which is the second term. And if I plug in 15 there, 15 times 3 gives me 45, which is the third term, and so on. Looking at the second example, again, looking for a pattern. 100 to 50 is being multiplied by a half or divided by 2. 50 to 25 is being multiplied by a half as well. 25 to 12 and a half, again times a half. And 12 and a half to 6 and a quarter, again times a half. Again, confirming that this is a geometric sequence because we're multiplying. So explicitly, we would say a of n equals 100 times 1/2 to the n minus 1. Now, I didn't do this one in the last one because it would have been a fraction, but this would be equivalent to a of n equals 200 times 1/2 to the n. Because if I went back to the 0th term or the initial amount, that would be 200. And if I plug this into my calculator and pull up the table, 200 will match up with 0 for the x. All right, and then recursively, we have a of n equals a of n minus 1 times 1/2, where the first term is 100. And again, that would generate the sequence. If I plug 100 in for all of a of n minus 1, and multiply it by half, I get 50. If I plug 50 in for all of a of n minus 1, I would get 25, and so on. All right, so again, typically you're not going to see these kind of sequences in a table format. So let's see what it would look like. So here, again, we have some patterns we have to look at. So -8 to -16, we multiplied by 2. -16 to -32, again, I multiplied by 2. And -32 to -64, again, I multiplied by 2, making my common ratio 2, and my first term -8. So explicitly, this would be f of n equals -8 times 2 to the n minus 1. And if I wanted to go further, this would also be equivalent to f of n equals -4 times 2 to the n. Those equations would generate exactly the same table of values or sequence. Here, -4 is just the initial term. Here, -8 is the first term. Okay, now let's take a look at recursively. And in that case, again, we would have f of n equals f of n minus 1 times 2, where the first term is -8. And again, if I plug in that -8, multiply it by 2, I get -16. Then I plug in the -16, multiply it by 2, I would get -32, and so on. Then number 2, 50 to 40. Ooh, that's a little bit tricky. So if you can't figure out what you're dividing by or multiplying by, multiply or divide the second term by the first, rather. So if you divide the second by the first, you'll figure out your pattern. So in this case, it's 40 divided by 50, which is 4/5. So 4/5 would be the pattern for 50 to 40. Let's make sure that continues. If I do 40 divided by 5, I get 8, and 8 times 4 is 32. So it is times 4/5 again. If I do 32 divided by 5, I get, use my calculator to show you. If I do 32 divided by 5, I would get 6.4, and I multiply that by 4, and I get that 25.6. So again, times 4/5. And we'll check one more time. If I do that divided by 5 and then times 4, I get 20.48. So again, it's times 4/5. So we get explicitly a of n, we can use that instead of f of n, but it's really up to you. Just have to know that they're the same, equals the first term 50 times 4/5 to the n minus 1. Or recursively, a of n equals a of n minus 1 times 4/5, where the first term is 50. So again, I hope you're picking up how I'm getting these equations. You're going to try some on your own. Make sure you're checking in with me so I can be sure that you understand this process. And we're going to continue doing this for a couple days. You will get it, I promise.